All right, it's 4 o'clock, so maybe we should get started, and more people will come in, but let's just get going. So, welcome everyone to lecture 6 of CS 545, the introduction to robotics. So, yeah, today will be about Bayesian filters, and the reading for today is section 2.4 of one of the textbooks on the website. So I have the physical copy here in case you want to buy it. You can also find some versions online too, I think. Hi, logistical things. So lab 1 is due February 4th. So hopefully, since we told you to get your project team by on the first day of the class, hopefully you're just about finishing up lab 1. If you don't have a team right now, then that's not good, but try to find one right away. On Piazza, I still see some posts there that have open searches for teammates. So if you still need a team, please check that. But otherwise, I hope lab 1 is going well, and we just released the assignment on Gradescope. So if you submit the PDF, you can just submit that there. And I think there were also some other questions about like how do you submit labs and what should you do. Then I think we answered that on Piazza, but just keep asking there if you have some questions. And for the homework, so we're working on grading homework 1. We're about 40% done, so it should hopefully be done in a few days. Then we'll release homework 2 soon, maybe tonight or tomorrow. Then we'll make it due in roughly 2 more. Yeah, and generally speaking, for all the assignments and the lab, the regrade request policy is no, you can request regrade because I know that if we made a mistake in grading, you should get the points back. But we do restrict it, so you have 7 days after we give you the grade, and then you can go on Gradescope, request the regrade function using there, and then we'll look at that. But just do it within 7 days of returning the grade to you. Because otherwise, what I found is in the past, if you don't have that limit, then what happens at the end of the course is students see that they have an A-, that they're half a point from an A, and then there's a long line of people who come to my office at the end. So we're just trying to make sure that you just request it within a reasonable time span. Yeah, any other logistical questions? I have the document open, but I see no one has typed in anything yet. Any question before we move on to the technical portion of today? All right, then let's move on. All right, so we're talking about Bayes filter today, but just to briefly recap what we talked about in the last 2 classes when we discussed Bayes nets, which we will use in the Bayes filter. So Bayes nets, if you remember, they help us encode conjoint distribution in a more compact way, where like if you have a joint probability, then instead of using the normal chain rule to factorize it, you can use the chain rule, but then you can remove anything that's not apparent when you're conditioning on something. And that makes your probability table a little more compact when you try to represent the joint. Yeah. And based on a Bayesian structure, based on like the node and where the arrows are pointing, you can guarantee certain independent assumptions from just looking at the Bayesian graph. Yeah, without knowing the details of like the conditional probability table and the numbers that go there, just from the structure, like the node and the graph, the edges. Yeah, and you do that with the D separation procedure that we talked about class, though, some of you wanted to see more examples, so I tried to get some more examples here when we talk about the Bayes net that we discussed with Bayes filters. Yeah, and then so remember also that we talked about like what independence assumption or conditional independence assumption were guaranteed from the graph structure versus those that were not guaranteed, but which could be true. Like you can have certain independence assumptions hold based on like actually looking at the probability numbers. All right. So today we'll be studying Bayesian filters or Bayes filters. All right. So when we discuss today's lecture as well as the next few, we're going to be thinking of a robot that operates in some environment where there's like the state of the robot plus the environment. That's like everything we need to know about the environment and the robot in order for us to understand the important details that we care about. And so we're going to denote all those states using x. So like xt is the state at time t, then xt plus 1 is the state at the next time. Yeah. So this could be like information about where a mobile robot is when it's trying to navigate through the maze. Yeah. So this is one of those causal chains that we talked about last time where we had like 3 nodes and an arrow going from one to another. And if you recall, like the guaranteed conditional independence assumption from this, it is if you condition on xt, then the probability of xt plus 1 and xt minus 1, they're independent. Like so formally, it's xt minus 1 and xt plus 1 are conditionally independent given xt, which blocks the information flow from from these two. And we are also going to be making the Markov assumption when we talk about state as well as other information here. So that basically means you just need to know like the information of the state at the current time. And if you know like xt, that's all it takes for to like make predictions about xt plus 1. So everything before that doesn't contribute to our knowledge. And mathematically, we can write that as follows. So if we want to know what is the probability of state xt given all the preceding ones, so that's here, it is just simply probability of xt given xt minus 1. And you can also like deduce that from the structure of the Bayes net. If you just imagine like a straight line where you have nodes like one pointing, each pointing to the next one. Yeah. And we are also going to make assumptions about stationary dynamics. So that just means whatever t is, you can always change the t to be something else like t minus 1, and then this thing should be true. Again, these are assumptions. So you might be modeling a robot in an environment where maybe you don't think this holds. Then you should not make this assumption. But to make things simple, when we talk about Bayes filtering today, we are going to make these assumptions. Yeah. Again, might not be true for your specific domain. If that's the case, you should take that into account when you design your model. All right. So another way that you could model transition, but we're going to use that a little bit less for this class, but you could use it depending on if you think it applies for your domain that you're studying, is to consider a second order model. And that means the Bayesian structure might look something like this. So xt plus 1 could point to xt, so it affects, in some sense, it causes xt plus xt, but you can have a second arrow that points to xt plus 1, right? Yeah. So what is the state transition probability in that case? So I'll let you think about it for a few seconds. Yeah, so you have something like this. So probability of xt conditioned on all the preceding states is going to be equivalent to if you just condition on the prior two states instead of the prior one. Again, you can look at that from the perspective of, look at the Bayes net and see that x, like if you have xt, well, maybe xt plus one is going to be easier to visualize. If you have xt plus one and you like shade in xt minus one and xt, which is like you're observing them using the terminology from last class. If you're observing them, then that blocks the information flow from anything prior to xt minus one, so that it doesn't, there's no active path from anything earlier to xt plus one. So that's why you can, make these assumptions. Yeah. Again, this is an assumption. So if you want to do a second order model for your own robotic domain, you should go ahead if you think that assumption is justified. If not, don't make that assumption, but you should at least know, like, if you make these assumptions, what are the probability distribution going to be like? Like that is a little more, I think that's more important than, thinking about, that we're always going to have this model, or maybe we're always going to have the prior model. Again, it depends on, your own assumption, whatever you're modeling, and yeah, other factors. All right, so these were the states. So that's what we denote as xt, right? But there's other things that we're going to assume. So we're going to assume that the robot can do stuff, because if it doesn't do anything, it's not really interesting. So the robot is going to execute action at each time step. So here we denote this as ut here, like the action at time step t is ut. If you're reading stuff about like reinforcement learning or things in that domain, you'll probably see like at instead of ut. As long as you know what it means, it should be okay. Yeah. And the way that we will assume this affects the state is that for every given time step, you have ut, that's the action that the robot takes at this time step. Then it'll in some sense call xt along with xt minus one, because the current state should depend on, what the state was like at prior time step plus what the robot did. So now if you look at this, what are we assuming when we think about the transition function dynamics? Like what is, in some sense, what is the probability of xt here? Like if we condition xt on everything, no, before it and this Bayes net, like what does the probability turn into? Yeah. Hmm. Seemed like a quiet day. So yeah, you have probability of xt conditioned on a parent, xt minus one and ut. And you don't need anything before that, because if you want to know like ut minus one, like it's not going to affect things, because if you condition on xt minus one, you block the information flow from ut minus one to xt. Yeah. And also just be careful if you're looking at some other textbooks or other classes, they might use the notation that, you have ut minus one here, like xt minus one and ut minus one, they both affect the state, so you get to xt, but the book that we're using uses ut to affect xt. So just keep that in mind when you're thinking about notation here, but we will follow this notation just because it's just the one that I have in the book here. All right, so in addition to the state of the robot and the environment, along with the action the robot takes, yeah, question? Do you want to go to the back of the previous slide? Yeah.
action UT happens on xt minus 1 time, which affects xt.
All right, so your question is like, when does UT like happen in something? Does it happen at like at time t minus one or t? Yeah, so the way this is written, we assume that UT is an action which happened like before xt. So if you want to think of it as happening at time t minus one, I actually think that intuition makes sense. So you have the state at time t minus one, and then you take an action, during that state, which the book uses UT for that. If you want to use UT minus one, like I think that notation is reasonable, but just be mindful that, for this lecture, all the math is going to use the notation expressed in the Bayesian here. So, yeah. Right. So we are also going to assume that there's some kind of sensor model. So if you remember from a few classes ago, I mentioned that, there's the notion of the state, which are the x's here. The states are usually like treated as ground truth information that we can't exactly know. So the state xt might be the exact position of a robot that in some kind of home or a warehouse or whatever, but we might not know like its real exact position, but we can have a sensor like a GPS unit or something else that gives us a noisy approximation of where the robot is. So these sensors are going to be denoted as ZT, right? So this is the sensor reading that we get when we measure the sensor while the robot and the environment are at state xt. So, and again, this happens for all time steps that we're considering. So, you should think of this, Bayesian as like extending out to the left all the way to 0, and then going forward as long as we run this model. Yeah. Oh yeah, question?
So why is the arrow pointing from the state to the sensor? Would the sensor tell you more information about the state?
All right, so your question is like, why are the arrows pointing from X to Z? Yeah, all right, so the way to think about this is these are like different things, like maybe Z is information from a camera that you get when you look at something that represents a state. So xt is like this ground truth state, like the exact position of the robot, the exact position of all the objects that it's interacting with. But then you get a camera reading, and then in some sense, the real state is going to affect what you see in your sensor reading. So it's like the information from the ground truth state is, in some sense, it kind of causes the reading that you'll see in your camera. Because if the object changes, you're going to see a different thing in your camera. Yeah. So, yeah, so at least for this class and for many of the other classes, this is the general model of the robot, the action, the environment, the sensor reading. Like this is the general model that we'll assume. Yeah. Again, it's just a modeling assumption. You may disagree with it for your own domain. If that's the case, you should recommend or propose a different type of Bayes net. But we're going to assume this Bayes net here for today. Yeah, and then the sensor probability reading. So again, you can use the assumption from the Bayes net structure. So probability of ZT, the probability that your sensor reading will give you like this particular camera or camera image or this particular like number in like a sensor that denotes position. That probability, if you condition on everything that happened before it, it just relies on xt. Yeah. And again, you can see that in the Bayes net structure. So if we were to shade in xt here, then ut, like the information will not propagate from ut to vt. the information from xt minus 1 would be blocked as well. So there's no like active path from anything before xt. Yeah. All right. So here's the Bayes net. To summarize what we just talked about, it will characterize the evolution of the control, the state, and the measurement. And it'll make assumptions that simplify all the conditional independence assumptions. And for this, if you're looking at this Bayes net here, like the book has actually shaded in the U's and the Z's to indicate that they're like observed or known, because U is like what the robot does, so you kind of should know it, and then Z is like the reading that we get as well. So it's also something that's observed. And the main thing that's not observed is what the state is, the X. Yeah. Yeah. And then we have the stationary dynamics assumption. We have the Markov assumption on the state and the measurement too. All right. So any question about this model up to now? All right. All right. So let's talk about belief. A belief is going to represent the robot's internal knowledge about the environment state, right? So again, the state is like this ground truth information. It can't be known exactly, but you can approximate it. And then the robot can have some kind of distribution over its belief. Well, really, the belief is kind of like a distribution of the robot's knowledge of the ground truth state. And another way to frame it is that we will assign some probability to each hypothesis about the true state. So it's easier if you think of it in like discrete land, where you have like a set of discrete states that the robot could be in, then your belief would be like the probability for each of those states. Yeah. And some of the notation that we'll be using today are this belief term. So we'll use BEL to denote belief. But if you want to think of it as this probability instead, you can do that as well. So it's like the probability of state xt conditioned on all the prior, sensor reading and all the prior action that the robot took. So that's just some belief. And then we'll also consider this thing. So it's like belief with the line above it. And then that's the prediction of the state before incorporating the measurement update. So you have the probability of xt conditioned on all the information to the left, but we just don't include ZT. Yeah. So if you're wondering why we care about the number or the probability, because in Bayes filtering, we have the term in the algorithm which get recursively updated based on the prior belief. And so this is just a way for us to write things out a little more compactly and maybe with a little more intuition. Yeah. So I'll repeat the definitions of these in the subsequent slide so that you'll have to memorize like what this means. But yeah. But just if you want more intuition, just think of the line here and saying, belief before your measurement, and then you go from here to here. All right. So Bayes filters. So this is a very general algorithm for calculating beliefs, which we talked about in the last slide, what beliefs mean. And here's what it looks like. So it's about 6 lines. If you include the algorithm, then no, 6 lines. So it seemed like a very simple algorithm. And if you notice, it's also recursive. So your belief of xt is calculated from the belief at xt minus 1. Yeah. And then the next step for us to understand how this works is to really show that the math here in line 3 and 4, that it correctly computes the belief at time t based on your current belief at time t minus 1. So if you look at this carefully, it shows one iteration of the algorithm at time t. So if you're at time like t equals 0, which is the first thing, then you'll need some kind of prior distribution. So if you assume nothing, you might want just a uniform distribution. Or if you assume perfect knowledge, you might just put all the probability math on like one state. Or in one region if you're in continuous land. Yeah. All right. And then again, it takes in the belief at the prior time step, what the robot did, the sensor reading. And for every single state, this should already be giving you alarm bells, but let's just assume that we can do this. Yeah. So for all your state xt, you do this computation. So you compute the belief before you get the measurement, which is based on this integral. If it's in discrete land, you should just do a sum. And then the next step is to incorporate the measurement too. And everyone knows what the eta term is, right? Yeah, it's just a normalizing constant. So this thing is in general not a probability distribution unless you put in the eta term. Yeah. Yeah. So why did I say that this should already be, giving you alarm bells? Like what is already kind of worrisome about this? Yeah, so if you're iterating over all possible states, then what happens if the number of states is like close to infinity or something very large, right? Then it already seems like there's some weaknesses to this. There's also other problem with this that you'll see later. So one thing that you'll see is that the Bayes filter is very general, but it also makes very few assumptions. And in general, this thing is very hard to apply to real robotics problem. You can apply it to toy problem, which we'll do later just to understand it better. But just keep that in mind when we think about like the strengths and weaknesses of different algorithms. All right, so let's do the bottom bullet. So let's show that it correctly computes the next belief or the current belief from the prior belief. All right. And the way that we'll do this is we will start with the computation for a belief here. So again, if you go back, that's this thing here. And then we're going to try to show that it equals this. Yeah. So that it didn't come out of nowhere. All right. So this is your probability of xt conditioned on the prior action and the sensor reading. Yeah. And again, the assumption here is that xt is complete, which means it gives you all the information you need to know to predict, like, the next state. Did everyone see what we did here? So we just took this and then we divided the z's from 1 to t to zt and z1 to t minus 1, right? So we just took that long list and then we just said, all right, the last one, we're just going to leave you alone. Yeah. By the way, we're also starting from 1 here, but you could also argue maybe you should start from 0 here. Like that distinction is not really important for here. All right. All right, and then the next step. So remember, the whole point is to try to manipulate the algebra a little bit so that we can express the right-hand side as something in terms of the prior. So, so you have base rule, right? Everyone see how we go from this line to this line. Yeah. I mean, the way that I do it when I'm trying to think about this is I basically ignore all the u, then all the 1 to t minus 1, all the z1 to t minus 1 terms, and I just think of zt, right? And then it's just xt and zt. So I do Bayes' rule, and then after that, I can add everything back into the conditioning. Because if you're consistent and you condition on different things, you can do that as long as you're consistent and do it with every term. Yeah. Yeah. So maybe let me just show this a little bit. So yeah. So again, just think of it, if it's easier, just think of it like this, just ignore everything that's commonly conditioned. Think of this and then just put in the conditioning after this. So yeah. Yeah. All right. So everyone see what's happening here, right? We kept the numerator the same, and the only thing we did is ignore the denominator. Yeah. So you'll see that's often what people do when they use Bayes' rule, like they apply this formula, then they dump the denominator, because usually it's not that necessary for some kind of problem for the problem that people use when they use Bayes' rule. Yeah. All right. So the next line going from here to here, there are 2 steps kind of mixed together. So, and again, this is a sum, but you could have an integral if you work in continuous land. Here we're going to make it discrete because sometimes that's usually easier, I think, for people to do to think about. So we went from probability of ZT conditioned on all this stuff, but you can just remove everything that's not XT, right? So you have XT here, sometimes it causes ZT, and by the structure of the Bayes net, or equivalently by the assumption that XT is complete, then this thing blocks all the information flow from everything before. So you can convert this into this thing. Yeah. Yeah. And for this term, you have probability of XT conditioned on all this information. So what happens here is like we've introduced XT minus 1. So we've introduced this sum over XT minus 1, and then we just put it in there, right? So this is just the law of total probability. If you have some probability of variable A, you can always do that thing is equal to the sum of all the probabilities of A and B, if you're summing over B. So just the definition of total probability, or if you want to think of it as marginalizing out the XT minus 1, you can also think of that. But you kind of see, you see why we have to introduce xt minus one, right? Because this is a recursion. So if you want to, like, if you want to show that this equals something as a function of, the prior time, you kind of have to introduce xt minus one somewhere. So this is how we introduced it. Yeah. All right. So again, what's the next step? So the only thing we're changing is the term that's inside the sum here. So we're just applying, the normal chain rule. So it's probability of A and B, you divide it like this. And again, just ignore everything being conditioned on, just think of xt and xt minus one, and then you could just condition all the common stuff after that. So yeah. So again, this is why I in the probability class, I spent so much time talking about, like, if you condition on something and you're consistent with how you use it, you can always, like, put in more things in your conditioning, as long as you put it in all the terms in your equation. Yeah. Yeah. All right. So the next step after this is that, again, we assume that xt is complete, right? And then what that means is this term, you can just assume that you'll condition on xt minus one and ut, right? And you need the ut, right? Why do you need the ut? Yeah. Because, like, you might naively think, well, xt is complete though. Like, if xt is minus one is complete, then why not just condition on that? Yeah. So why do you need ut? Yeah. Yeah. So basically, the action is necessary to the action is going to, like, affect the xt, right? So yeah. Yeah, and if you want to look at it from the structure of the Bayes net, like using the independence assumption that we covered last week, that's also possible. All right, what about this thing here? You have probability of xt minus one conditioned on all of this stuff. So if you have xt minus one and you're conditioning on, like, sensor reading from t minus one all the way, to the earlier one, what can we throw away from here? Yeah. If you just look at the structure of the Bayes net, then you have xt minus one. The parents are ut minus one and vt minus one. But ut is not a parent of xt minus one. So it doesn't make sense to put ut here, like the last term in this whole thing, right? And so that you can go from u1 to t to u1 to t minus one. Yeah. All right. Any questions about this? And what do we have now? Like, what is this term? Yeah. The I think I might have to say that again. So, yeah. So the previous belief, right? So you had p of xt with no, it goes from it's xt and everything goes from one to t. You have xt minus one and then the v then u that go from one to t minus one. Yeah. All right. So you put it all together. We have this. So you have probability of xt given all the sensor reading up to the current time, all the action up to the current time. That's the same as the belief at xt, right? And this thing here is straight from the last line on the prior slide. So you have probability of xt minus 1 conditioned on v 1 to t minus 1, u 1 to t minus 1, and then that is your belief of xt minus 1. Yeah. And then you get belief here, then belief of xt minus 1. And if you notice that we have this thing here is basically the belief where you had a line over it. So it's before we took the, it's like without the sensor reading, right? So if you look back at the algorithm, you have this, right? The belief here is the integral of the transition probability on the prior belief without the line. And here, this is the sum of the transition probability and the prior belief, right? So the only thing that's different is like, we have a sum here, they have an integral in their formula, but it's the same thing. Yeah. All right. Yeah. So, so again, yeah, you have the pseudocode here. What we've just shown is that if you take this math term and then you expand it out and then express it as the prior belief, then you get something that's exactly this. So belief of xt is equal to the normalized, probability of, the sensor reading times this term, which consider the transition probabilities and for each of the prior states, right? So another way to think about this is if you have your belief here and you have the belief before you incorporate that measurement, then for every xt, you're essentially weighting it by like what is the probability that you get this sensor reading given that we assume we're in xt, right? And your whole distribution is going to be this thing when you consider the whole span of like what can xt be equal to. Yeah. Just be mindful that, if you're trying to match this exactly, the notation is a little bit out of order. Like we have xt minus 1 and then u, but they have u and xt minus 1. So just be aware of that. That ordering doesn't matter. Yeah. Any questions or issue with like intuition or like how this works? So, yeah. All right, so you're asking what is the purpose of like the sum or the integral here? All right, so what this is doing is this is considering a sum over all the possible values that your random variable representing the state can take on. So imagine you have two states. We'll get to an example later, but like you have two states of the door. Is it open or is it closed? And this helps us to, like, we have to account for the probabilities of all the possible values of the state. So this is it's just a way to like consider all the possible values of a random variable, right? So just think of it as analogous to like marginalizing something out in probability. Like you can always do, you know, So that's some probability. And if you have another random variable, you can only, this, you can make this true because you're considering every possible value of what B takes on. So, and I guess for this thing here, you can think of it as, well, our belief about what is at the current state needs to consider, well, what are all the possible values that the prior time step belief could be at? Like, you have to consider all those possibilities, and at the prior time step, the robot was at, this state, or the environment was at this state. What's the probability that the robot action led it to what we think is what is the current state? So this is another way to think about it is, I think, to get the environment at some current time step, we have to consider all the possible values that the state could have been at the prior time step, weighted by the probability that it went from like this state to the current state. So again, think of the current state as like whether the door was open or closed. The prior time step, the state could have been at either one of those, door open or door closed. Then we need to consider probabilities of if the robot did something, and we're considering, what is the belief that the door is open, then what the weighted probability of prior time step, the door was closed, did the robot make it go from closed to open, or did the robot actually make it from open to open? Yeah. So yeah, hopefully that intuition is somewhat clear. All right, anything else? All right, and we do have an example. The figure is a little bit, not very detailed, but hopefully the example will help you see what's going on. All right. Yeah, actually, we're roughly about the halfway point, though. I think it's a good time to take a very short break, maybe 5 minutes, and then I'll leave the slide up here so that you can look at it in a little more while the break is happening. So yeah, let's take a break, and then we'll be back in about 5 minutes. And yeah, happy to answer more questions if you have them. Do you have a question? Yeah, let's talk about it. I'm gonna bring. I'm still confused about why do we need to do that. So this is just on the constant. It's an arbitrary constant that has those normalized. So the reason is this one is a probability distribution, right? So if we dump the numerator, then we can change all the values here. But let's do an example. So this is a probability distribution, right, over 3 variables, because it's sum to 1, and everything is non-linear. So like the probability that this random variable takes on the first thing is 1. So if you do what we just did, that is an example of removing some, so we remove some factor common to all these. So this could be like, let's say that we divided everything by two, right? But this is not a distribution, it's not a common distribution, it doesn't come from one. So it's like so this this thing here, like it, yeah, again, it's like you just remove something, you remove the common factor. So yeah. So this data term is just a way for the right thing in a shorthand. Sometimes people do the proportion to, have you seen that? Like, yeah. Also, I don't say that when, I think it's the class, but when you go from the line, the data might actually change, but the real, I don't want to be confident that you have changed from like this line to this line, but you just use the same data to make it. Representation. Let me explain that. The anchor right here will change gradually because we will add a new item into this form. But to express this as a project, so we just put it as a deposit. So we can ensure that it will feel like the whole of the here is right in order to grab from the. I don't quite understand for the values. It's not going to change. It could change when you go from line to line. So I guess if you really wanted to be precise, you could use it like data one. Sometimes you have data two, which might change. So again, this is just a shorthand notation and just a way for us to do the math while realizing that sometimes don't matter. But we still, for us, still writing the quality of a system type, there's just some constant such that like if you have this here, there's just some constant that we multiply every time here, you get a distribution. But yeah, it's just a way of thinking about it. Yeah. What are we doing? All right, maybe 2 more minutes. Yeah. I think it's a weak question. Oh. The reason for the backlash is because in latex, you have to write the backslash together to render it. All right, so maybe let's get back to the lecture. So, um, so yeah, hope everyone had a good break. And just to clarify some stuff that might have come up. So when we have this formula, then no, this eta term, this is how you spell it. We call it eta. I think that's how you pronounce it in Greek. So when we have that eta term, when you go from line to line, it might not be the same constant in general. I think for these lines, it's actually the same because we're using exact probability rule. But if you do something like jump a normalizing constant in one step, you have eta. If we were to do something similar in another time step, the book would still use eta. So you might not, like they wouldn't do like eta 1, eta 2. They would just use the same Greek letter to indicate any normalizing constant. Yeah. Yeah. Yeah, and need the normalizing constant because if you dump the denominator, it's not a probability distribution anymore. All right. So up to now, we covered the derivation of the Bayes filter. So let's try to conceptualize it with an example. So we have the example of a robot. So this is our robot. And the state that we're going to consider is the state of a door. And the sensor is on the camera. So the camera reading will tell us like information about the state. So we make the following assumption. The states can be either open or closed. So again, this is a really simple robotics problem. The state has like nothing to do with the robot here, it's just whether the door is open or closed. And the robot doesn't know this exactly, but it can use sensors to try to compute probability about what is the probability that the true state is door is open, or true state door is closed. And so to make it a little more clear, the observation will be sense open versus sense closed. Yeah. And the robot's action could be push or do nothing. So maybe just imagine that the robot is like next to the door and it can push its arm and then the door can potentially move or not. Or the robot can do nothing. And to make things interesting, because usually to make things interesting for Bayes filters, you have to assume that there's some noise in your sensor, which is basically always true in the real world. Anyway, so we'll have a noisy sensor model. Probability of the sensor data saying, oh, we think the door is open, conditioned on the fact that it is actually open is 0.6. That's really bad, by the way. I mean, if the door is really open, then the robot sensor it only thinks that it's open like 60% of the time. But let's just assume that, and like if the door is actually open, then the probability that the robot like senses that it's closed is 40%. Right? It might be a little more accurate if the real state of the door is closed. So in that case, the sensor will say it is closed 80% of the time. So it's correct 80% of the time. And then incorrect word that it thinks it's open with probability 0.2. All right, so that's our sensor model. Yeah. So the sensor, they are more reliable in detecting a closed door. All right. So we have the state, the observation, the action. We have the sensor model here. We will also make some other assumptions about what are the transition dynamics. So the robot can use its arm to push the door. So if the prior state was door is open and the robot then pushes, then the probability that the door remains open is 1. So yeah, if you push an open door, it should stay open. And then, it's 0 for the other outcome. And then if it's closed and we push, then the probability that it's open is 0.8. Right. But again, when we consider the transition dynamic, like this was assuming that the robot pushes. We also have to assume that the robot could do nothing. In that case, what we assumed would be the true transition dynamics could be something like this. So if in the prior time, the door really was open and the robot did nothing, then it stays open, which seems reasonable. I mean, if the robot does nothing, you would expect most things to stay unchanged. Yeah. In fact, you get it's the same thing here. Like if the robot does nothing, the true state is going to stay the same, right? Like it should never go from open to closed or from closed to open if the robot does nothing. But again, this is an assumption that we'll make for the purpose of this environment and the calculation. I mean, you might think that for whatever environment you might be modeling, maybe there should be some non-zero probability of the state changing. If so, you should make that assumption when you're defining the transition dynamic. So. All right, so the Bayes filter at time t equals 0. Suppose that at the next time, the robot takes no control action. So again, I get this goes back to an earlier question. Really, this should be at time, it's more intuitive to think about it at time t equals 0, but at time t equals 1, we're going to assume that the robot did like U1, which is the action that leads to the time t equals 1. But anyway, the robot takes no control action and senses an open door. What is the resulting posterior belief x1? So how would we do this? Like what are the steps to get started with? You'll probably have to do some of this for your homework or some exam. So just um, all right. So there's a question that says, how do we get the value for what are the probabilities of the robot taking an action or doing nothing? So, well, all right, there's 2 ways I can think of answering this. So the first interpretation of how do we get all the bottom probabilities, right? So that's one interpretation of the question. Like, how do we get the numbers? And the answer is, well, usually you're gonna have to assume that they're given to you, or you have to like compute them somehow. So again, this is just like some kind of transition dynamic. Like for every given state, the robot does an action. What is the next state? So like here for this, I'm just giving it to you. And if you wanted to like compute it, you might need to like run the robot in some environment and compute your data and then from your data, you can compute the probability. Another way to interpret it is, well, how do we decide whether the robot should push or do nothing? Because I gave you the table, but we didn't discuss, what is the probability that UT is push or UT is do nothing. And that's more of a matter of like, you have to have a robot that will do action, right? And you might hand code the decision making. Like I call it a policy, like like many people in machine learning and robotics do. Like we have some kind of policy that determine what is the action a robot should take. But that's something that's a little bit separate for the purpose of today's discussion. We're just going to assume that the robot did something, and we want to compute probabilities from that. When we get to the next few courses and the end of the course, we will discuss ways to try to get policy so that we can determine like what is a good action to take at a given time step. But for today, let's just assume that we give you the action the robot is taking, and that we give you these tables. So. Hi. So the question here is, what is the resulting posterior belief of X1, right? So again, think about what that means. That means we have to know like what is the probability that the real state at time t=1 is door open or door closed. So what is the robot probability distribution for that? But before answering that, we actually need a prior belief because we need something to start out. Like before the robot does anything, we kind of need something that we can use to begin the recursion that's in the Bayes filter. So the most boring one, but maybe the one that makes the fewest assumptions is let's assign equal probability. So we'll assume that the robot's belief that X0 is open is 0.5. Same thing for X0 is closed. So maybe for your particular domain, you might have good reason to think that, well, these aren't the real probabilities. In that case, you should change the prior so that it reflects your belief before you do any computation. All right. So now we're on the Bayes filter examples here. We've assumed an equal prior over the possible state at time t=0. These are the various probabilities that we recorded. Now we're showing the do nothing here because we're assuming the robot takes no control action. So we have no control action. So that's why we have this here. So again, the question is, what is the resulting posterior belief X1? So now that we have our prior, like how do we go from here? Like, yeah. So remember that the Bayes filter, if you apply the Bayes filter algorithm, the first step was compute this thing, which is like the belief of the next state before you take any measurement into account. So the only thing it takes into account is what was the prior state and what action did we take to lead to X1, right? And if you factor this, if you write out this more explicitly, because x0 only has two possibilities, right? It would either x0 was open or it was closed. Yeah. Yeah. So what is this value here? I think I gave you the number to compute it. Uh, yeah. So what is belief with that line here of x1? All right. So I would it was kind of misleading to say like what is the value. So if I say like what is this thing belief overline of x1, you have to say the full distribution, right? You have to say like what happens if x1 is door is open, or what happens if x1 is door is closed. So you have to give me the values for both of them. One hypothesis, x1 is open. This is the value here. The probability that x1 is open conditioned on the prior state being open and the robot doing nothing, weighted by the belief that it was open. And same thing here, but if you assume that x0 is closed, right? And if you plug in the number, you get 0.5. So this thing here, the belief here, the prior is uniform, so it's 0.5 for both. And if you do nothing, you should go from open to open with probability 1. If you do nothing and you go from closed to open, that shouldn't happen by assumption here, right? You do nothing, door at the prior time step is closed, it should not be open. So it has 0 probability. What about the second hypothesis? What's the value? 5 seconds. Yeah. Yeah, great. So, but what did we accomplish here? It seemed like we went from our prior belief of like 0.5 and 0.5 for both, but we didn't really, things didn't really change here, right? It looks the same. Now, why is that? Because no action was taken. Well, right, the no action was taken. The action is really do nothing. So yeah, I guess you can argue that way, but my bigger point is that that we didn't take into account the measurement yet. So we didn't take into account like, what is the robot updated information? Yeah. So, after we process the control of the action being do nothing, then we went from the prior to the updated belief. But it's this is kind of meaningless because the robot's action did nothing. We didn't incorporate the measurement yet. And there's also no sensor noise. Or there's no noise in the transition dynamic. If there had been some noise here and was like non-uniform, like not the same for open to close or closed to open, then you might have gotten something different. But if you assume like a symmetric noise in some sense, then you'll get this thing. What should happen when we take into account the measurement? Yeah. It should not be uniform, right? Otherwise, the measurement is kind of like meaningless. Yeah, question?
We already were five X one day.
So your question is the belief of x0 always equal to over bar belief x1? In general, no. Because here's what. There could be values of the action that, like, I think there's ways that you can plug in the numbers for the transition probability that would mean that, like, if you do nothing, then it's more likely that the state will like transition to like or funnel to something that happened if the robot does nothing. Here we're not doing anything that complicated, but like if you fiddle around with the numbers here, then you might get a change in that. Like, I mean, again, if there's no noise in the transition dynamic and doing nothing really doesn't change the state, then they will be equal. It's just that in general, you do have to do these computations because they depend on your transition dynamic.
Is there some? These two beings, how do you see that?
So is there something like in between the, I guess I'm not really sure what in between means. They're like maybe I think the way that I'm trying to think about this intuitively is that for the belief for the for the for this thing to be different from this, if we did nothing, then think of the transition as like there's always going to be more probability for like going to a certain state. So imagine that something's strange with the physics of the door, and if you do nothing, it always assumes that the door is going to close itself. So there might be more probability of like if you do nothing, and the door is open, it might actually close. So you might get something different if you plug in the numbers. Yeah. Yeah. In general, yeah. Yeah. Again, our updated belief is equal to the prior belief. But now we're going to incorporate the measurement. So the measurement that we got from the robot sensor that Z1 is open, right? So the sensor reading suggests, that the door is open. But then what is the updated belief probability? Well, intuitively, it should show that there's more probability for it being open. But let's actually plug in the numbers and see if it does that. It should do that. Otherwise, it's a strange sensor. So again, this thing came from the definition of the Bayes filter algorithm. So you have the belief of xt is equal to some constant times the measurement probability of seeing that ZT was open, given that XT was, or given that XT is whatever it is. Like you have to consider both possibilities because we have a probability distribution. So, and then you also multiply the belief before you take into account the measurement. Yeah. So if you plug in the numbers, then for the belief that X1 is open, then you get this thing here. What about X1 is closed? I'll give you a couple of seconds. Yeah, the Google Doc is a bit quiet today. Yeah. So eta of 0.1. Yeah. So close, but yeah. So we have the prior here. Then you have v1 open given that x0 is open, and then that is 0.6 here. Then v1 is open, x0 is closed. That is where that is this thing here. Yeah. So what is eta here? What is eta? Uh, yeah, so if you, well, I actually don't know what value it is. Like my point is, I guess my point was like, whatever eta is should result in this normalization, right? So the way to think about it is this thing is it 3 times as much as this thing, right? So if you normalize it, this probability should be 3 times this thing, like 25 times 3 is 75. So yeah. So the same relative values hold. Yeah. All right, so what happens here? What does this suggest intuitively? It's not uniform, right? Like there's more probability for x1 is open. Does that make sense? I mean, you did nothing. The sensor reading said door is open. Yeah. So again, if this thing was 0.5 and 0.5, it would seem like a strange sensor. But here the sensor is noisy, but it does give you the right answer more than 50% of the time. So intuitively, you should have something like that. All right, so now we're going to move on to the next time step. Let's assume that we're going to do this for one more. So this will be the last time step. So I'm doing t equals 3 and 4. Like, I think that would be a lot for this example. So let's just do t equals 2. And that way I don't have to type up as much math to paste into the slide. All right, suppose that time t equals 2, again, if you want to think of it as time t equals 1, you can do that. If t equals 2, the robot pushes the door, then that is u2, and then that leads to x2. Yeah. Um, so what is the resulting posterior belief of x2? So again, when we say what is the resulting posterior belief, we really mean a distribution. So you have to give me two things. What is the probability that x2 is open versus x2 is closed? Um, yeah, so here are the newer probability distributions that you need because, yeah, now we're pushing, so we need to assume that as part of our action. And again, the Bayes filter algorithm, again, I'll show it here so that you can see it. Although if you already printed it out, then you've already gotten the algorithm. Yeah. So time t equals 2, the robot pushes the door and senses an open door. So what is the resulting posterior belief? So before we consider the measurement, that would be the overline. So you have belief overline with x2. And you have this thing here, belief of x1 is open versus x1 is closed. So we computed that already. Yeah, so what are the updated beliefs before you consider the measurement? Uh, yeah, I'll give you a couple of seconds to think about it. I think you should be able to do it just from looking at the numbers on the slide. Yeah. All right, so belief overline of x2 is open is this thing here, so it's the belief of the last x, so that means x1, and then you have to weigh it by like, was x1 open or x1 closed? So if x1 was open, then probability that x2 is open, given that x1 is open and u2 is pushed. So again, u2 is the action that led from x1 is open to x2 is open. So same thing for something similar for this, except if it was closed and you push, then what's the probability that that led to x2 is open? And then if you plug in the number, you should get this 0.95. And same thing here. So the belief that x2 is closed, you get 0.05. So yeah, this goes back to an earlier question, like is belief at the prior time, like always equal to the overlying belief at the next time step? Then no, because, well, here it's not. Like we went from this 0.75 and 0.25, we went from that to 0.95 and 0.05. Right. Yeah. So now we have to take into account the measurement update. So if you do that and you plug in the number, then, well, if you go back, so first, if you go back and you look at this, it's 0.95 and 0.05. So if that is our belief before we take into account the measurement, like what do you think the belief, the updated belief should be after the measurement here? Like what should the value, like will belief of x2 is open, will it increase or decrease from 0.95? Will it go up or down? All right. Well, I know what we're going to put on the midterm now. Yeah. So you don't have to give me the number. I just want to know, like, will this thing, will it go from like 0.95 and 0.05? Will it like increase the weight of open or will it decrease the weight of open? Yeah, increase the weight of what? Yeah, so why is that? You're looking at this thing, right? Yeah, so before we take into account the belief that the door was open, like then the next thing after that is to consider the sense of reading it, because we sense an open door, it seems like that probability should go up. So yeah. So if you do that, you get x2 is open, which is equal to some normalizing constant. I don't know what the value is, times probability that x2 is open, given that x1 is open, and the belief, the belief before taking into account the measurement is x2 is open. And then belief of x2 is closed. So again, it's the same thing here, except you change the belief to be closed. Yeah. Yeah. And then you change all the x's because like you have the same x here, so you just keep the x's consistent. Yeah, so what is eta here? I don't know off the top of my head. Although I know what you should at least be able to do like the math to um, figure out what it is up to like the multiplicative factor stuff. Yeah. Yeah, so after you normalize, it should be something like this. So the robot's belief of x2 is open is 0.983. So that went up from 0.95. Yeah. All right, so the question is, in this equation, should it not be x2 is closed or open instead of x1 when calculating belief of x2? So I don't quite understand the question here. I think, so there's multiple equations here, so I guess I'm not sure which one I'm supposed to be looking at. I mean, we have x2 is open and x2 is closed here. Like, this is the belief that we're trying to compute. Yeah. And like, we can't have x2 here because we're conditioning on something. Like, we don't know what x2 is, so we just assume that we know what x1 is, and that's the prior uh, x. Yeah. Oh yeah, so I guess I don't really know what the question is asking, but yeah, feel free to type it in again, and then I can look into it. By the way, there's a lot of math notation, so you might have seen that, though there's a good chance there might be some kind of typo. I tried carefully to make sure that there wasn't any, but if you find something, just let me know. Yeah. And I think if you're looking at the book has some cases when it's like XT underscore one, but if you look at the official list of typos, like they have that listed there. So you can always correct it if you go to the book's website and look for the errata page. All right. So do you have any questions, any last questions about this? Otherwise, we will just move on to like a high level example because I think we've gone through this enough. All right, so localization. So again, we're not going to plug in some numbers. We just want to give you some high level intuition here. So we have a mobile robot. We have a 1D hallway with 3 doors. So let's imagine that the state would be anywhere in this line. Like here, here we'll consider like a continuous state space. So it could be anywhere in the horizontal line. And that is what we mean by the state. So if we initially assume that we don't know where the robot is, or no, if the robot doesn't know where it is, we have a uniform distribution. Now let's assume that the robot can query a sensor. So the robot has some sensor that tells us like, is it adjacent to one of the doors or not? But because the robot doesn't know where it was originally, if all the sensor information gives you is that the robot is adjacent to a door, then we have to assume that the robot could be at either one of these 3 doors. And what happens if you were to go through the Bayesian filtering algorithm with like probabilities that we would have to provide to you. So again, we don't provide you with probability. We just assume that you'll get them from something, but we won't give them to you. This is just more like intuition in terms of how a Bayes filter should function under these assumptions. So if your observation told you that the robot truth state is like higher when it next to a door, then that's where the belief should be. Yeah. Yeah. So if you suppose that the robot moves to the right, then what will be the updated belief after that? And let's assume that we don't have any other sensor reading. So if you're just given this and you assume that the robot moves right, then what would the belief look like before you incorporate any measurement? Unfortunately, yeah, this is not something you could just like say. I think you would have to draw it out. Maybe we'll give you that as an exam question. I don't know. So if you compare this with that, then what happened is the belief should be something like this. So the robot moves right. And then the belief similarly shifts to the right. But it also has, like, if you look at the curve there, it looks less peaky, right? Yeah, so why is that? Yeah. So in general, we'll assume that whenever the robot takes an action, that usually increases the noise and uncertainty before you get an updated sensor reading that can provide more information about the state. So again, this is more like a general principle. I mean, you may argue that, well, there are some environments that maybe this doesn't true. But for the most part, we're going to make the assumption that if a robot takes an action, it's going to increase uncertainty. But if it takes a measurement, it's going to decrease the uncertainty. Yeah. So if we're asking you, we'll try to make the assumption clear so that you can kind of think about what to draw. And then with more measurement, the robot should be more confident of its location, which means, if it takes the measurement and it sees that it's adjacent to a door again, the belief here should be higher because it assumed that you had this as the prior belief. And so this one is higher because if the robot just moves right and then sees that it's adjacent to another door, then it's more likely that it went from here to here instead of like here to here. Or again, there are some assumptions here that maybe you can argue, maybe they're not true. We'll try to make the assumption clear to you if we ask you to answer something like this. Yeah. All right, any questions? Okay. Oh, yeah.
Based on this, the belief is the answer is okay.
Well, so are you asking like how do we like actually get belief of X? Like,
This is considering that we know there were 3 doors and we like the one
Yeah.
that door one before this action.
yeah, we do assume that there are three doors. So
And the door.
well, the robot knows the door only from the sensor reading, but we assume that the sensor reading showed robot is next to a door. So yeah. And by the way, if you also want to know like how to actually make these curves, like I think what the book did is they might have had some numbers or probability that they had, and then they ran the computation, but they didn't show us. So this is really more about like intuition and about how to think about your measurement belief, your measurement probability than the updated belief. All right, so if we go back to the belief formula and we think about what happened if we like an observation ZT. That would mean you have a graph like this. So you have UT and XT minus one, which cause XT, but you don't get ZT. Then how do we think about the belief? Like, how would we have to compute? So normally, it's like this. So this is the normal formula. I just copied and pasted it here. Like, belief of xt equals some normalizing constant times this thing multiplied by the weighted sum of the prior belief and the transition probability of going from xt minus 1 to xt. How would you like compute the belief of xt if you didn't have ZT? Yeah. I'll give you a second to think about it. All right, so what I would recommend doing here is our Bayes net would imply something like this. So because we don't have ZT, we can't really use it. So you kind of have to make it belief of xt equals some normalizing constant of oops, some normalizing constant. So it wouldn't be the same as the one here, but it's just some normalizing constant weighted by this. So essentially this means this is like, it's kind of like our belief overbar, like before we incorporate our sensor reading. Yeah, I think that's what the comment in the Google Doc is saying. Yeah. Yeah.
Basically, somewhat same with some noise.
It,
Be similar to like sensor value without the sensor value, considering there was some noise.
so it would be equal to the belief without the sensor value when you consider like noise and the transition dynamic. Yeah, so the noise in the transition dynamic would be embedded in this probability. Like you may or may not get noise. Usually, I argue you do, but if we're giving you like a toy example, maybe noiseless. Yeah. Yeah. All right. So what happens if you have two sensors, VT of 1, VT2? Then for a given time step, you might have a Bayes net that looks like this. Xt minus 1 leads to xt as well as ut, which is an action that leads from xt minus 1 to xt. You can just redraw your Bayes net like this. That is assuming that you have some conditional independence. So if you want, you can also just embed everything into like one Z, like one multivariate ZT, and then put everything in one node. I mean, in practice, your XT is going to be some big vector with a bunch of numbers that indicate all the interesting things in your environment. So, and then your belief will be something like this. So again, hopefully this is pretty straightforward. Like it's basically the same formula from earlier, but so if you go back to the last slide, we had probability of VT given XT, right? you can just plug in V1T and ZT1, ZT2. I don't know if you're supposed to say the exponent or the subscript first, if you have, I don't know, yeah. So you can have something like that, and then if they're conditionally independent, which this Bayesian actually does imply that they're conditionally independent, because it's like the same diagram that you saw last class, right? You had all right. So you have the common cause, right? Like this thing goes to here. And then if you condition on this, they're independent. Yeah. Any questions on that? All right. And then what happens if we don't supply an action? So the action is like a no-op. It can be a little bit tricky to think about, because sometimes your no-op is like, sometimes that is actually a valid action choice. And we assumed that in the robot example, where it could do nothing or it could open the door. Yeah. I thought, yeah, this is just a question to think about, like, how do you fiddle around with the formulas for the updated belief? And if you want, you could write something like this. So if the state doesn't change, if you don't supply an action, then you could rewrite this probability as like an indicator function. Yeah. Again, this would be if it's like a noiseless thing. So yeah. So this indicator function would be 1 if xt is equal to xt minus 1. Yeah. And that way, when we're summing over all the possible prior states, this sum reduces to like one term. It's really a sum over many terms, but all are 0 except one thing, which is 1, which is fine because that's a valid probability distribution. Like all zeros except for one that in one component. Yeah. All right. So to summarize, so again, Bayes' rule lets us compute probabilities that are very difficult to assess. Like that's why we often do we have one term and then have 3 others. It seems a bit strange, but like sometimes that denominator we don't care about, and then the things in the numerator, they're like a prior, and then things that we already know. And then under the Markov assumption, we discuss Bayes filtering, which is like a recursive algorithm for estimating the state. So again, the whole point here is we don't know the exact state. We have sensors, and then we have a belief over what are the states. That's a distribution. So the sad thing is that in practice, it's really hard to apply Bayes filters. So unless you're dealing with a really trivial case like what we covered here, so that's unfortunate, but the next class, the next one will cover more of practical variants. So see you Wednesday.